Hello everyone. This video is on the Knewton Alta assignment for section 6.6 part 2 called Solve Exponential Equations. So in this video I'm going to be going over a preview version of this particular assignment. So please understand, that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But the objectives are the same, the structure is similar. Alright, so I'm hoping that watching me do these here helps you in some way when you work on the assignment on your own. Alright, now on the assignment page you should be seeing the title, the mastery bar telling you how far along you've gotten, the objectives. Looks like there are 4 objectives in this assignment. Under the current objective there should be a question related to that objective, and at the bottom of every question you should see a feedback button where you can send feedback to Knewton if you wish. You will not have this instructor cheat button, that's for instructors only. But you will have a more instruction button. If you're ever struggling with a topic or a question, click on this and you'll be taken to a page with further reading or videos to study. And then you'll be given questions related to that instruction. And completing those questions is another way to get you through and progress you through the assignment. Alright. So the first objective I'm seeing, use logarithms to solve exponential equations. Alright, so I'm going to write out this equation here. It's an exponential equation because the variable we're trying to solve for is in an exponent or multiple exponents. And so I'm going to write out this equation and I'll discuss several ways you could solve such an equation using logarithms. Alright, so this first equation we're given, we have 6 to the x plus 3 power equals 8 to the x power. Alright. So, I guess I'll call this number 1, method 1. The first method is to use just log base 10 or log base e, because that's what buttons usually on most calculators. Is a log base 10 or log base e natural log. If two numbers are equivalent like this, right, these two expressions represent the same positive number. And you may recall that logarithmic functions are one-to-one. So if two inputs are the same, their outputs must be the same. You're not going to have the same input take you to 2 different outputs in a logarithmic function. So what I'm going to first do is I'll do the natural log. It doesn't matter. You pick a log of any base you wish. I'll do natural log. Take the natural log of both sides, and based on the fact that logarithmic functions are one-to-one, you'll still have equivalence. So the natural log of the number on the left, 6 to the x plus 3 power, right, should be equal to the natural log of the number on the right, 8 to the x. Okay. Then the reason we're using logarithms here is so we can apply the power rule. Now I'll apply the power rule for logs. Remember, the logarithm of something to a power, you can pull that power out and make it a product. So the natural log of 6 to the x plus 3 power is the same thing as, now I'm putting it in parentheses because the entirety of x plus 3 is the power. So it's x plus 3 times, and then just the natural log of 6. So it's x plus 3 times a number. Right, the natural log of 6 is just a number now, right? There are no variables in this natural log anymore. And then I'll distribute that number in a second. And then the same thing happening over here. The natural log of 8 to the x, use the power rule, pull that x outside, and we have x times, and then just the natural log of 8. And once again, like the natural log of 6, the natural log of 8 is a constant, it's a number. It has no variables, right? And then it's multiplied by x. So solving this equation is no different than solving x plus 3 times 5 equals x times 4, something like that. It's no different than solving that kind of an equation. Alright, so then we solve this equation. Over on the left side, I'll clear the parentheses, distribute that natural log of 6. So we have x times the natural log of 6 plus 3 times the natural log of 6 equals, and then on the right side there's nothing to do with, no parentheses to clear. I mean, there are parentheses around the 8, but there's nothing I can distribute. We just have x times the natural log of 8. And then I just, take all the terms with x to one side, terms without x to the other, right? This is actually a linear equation in x. The highest power on x I'm seeing is x to the first. So I'm going to take away this x times the natural log of 6 from both sides. And that gives me all the terms with x on the right side, terms without x on the left side. And so on the left side, I still have this 3 times the natural log of 6. And on the right side, since both of these have x in it, we could factor x out. And if I factor x out, you'll have x times, the quantity natural log of 8 minus the natural log of 6, which is a number. The natural log of 8 minus the natural log of 6 is some number. Punch that in your calculator. Figure out what that number is if you want. So now I have what I want. I have, x times some number equals some other number. And to get x alone, I divide by this number. So x equals, 3 times the natural log of 6 divided by this natural log of 8 minus the natural log of 6 number. And there we go. That's our solution. Now you could, of course, check. And I'll check this with a calculator, of course. But this would be called the exact solution. They did ask, put in either an exact solution or a solution rounded to the nearest tenth. So I'm going to put this into a calculator. Right. So I'm going to that Desmos website, desmos.com. Now I'm going to put in a equals, just for a variable's sake. Right, you don't have to use a if you don't want to, but 3 times the natural log of 6 divided by, and then in the denominator, the natural log of 8 minus the natural log of 6. And you see they tell us here a equals 18.68, which would round to 18.7. So this is approximately 18.7, our solution here. And we could also enter this if we wanted. They said enter an exact answer or the answer rounded to the nearest tenth. But check it, let's check our solution as you would with any equation. So I go back to the original equation. Remember I called this number a on the calculator. So on the left side I'll put in 6 to the a plus 3, and then I'll put in 8 to the a and see if we get the same value. So on the second line here, what's 6 raised to the a plus 3 power? 6 raised to the a plus 3. So it's a huge number, 7.4 something times 10 to the 16th, a very, very large number. And the other side was 8 to the x. So what's 8 to the a? And you see it's the exact same value. So this value of a up here, this 18.68 blah blah blah, is the solution to our equation. It makes the expression on the left side equal the expression on the right side. So 18.7, is a valid approximation of the answer. Now I'll leave this up because I do want to show you some other ways. Another way that I actually like, this way is fine. I just find that people tend to get confused by all the logs or ln's everywhere. They think they're variables or something, right? But once you've used the power rule like this, then it's just like solving a linear equation. Right? People just tend to mess up because they see all these logs all over the place. So let me show you an alternate method. So part 2, or method 2. Using properties other than the power rule. All right, here I kind of use the one-to-one property and the power rule and all that. But use properties, I want to use properties to get basically just b to the x equals some number. So I'm going to try to get it, I'm going to try to write my equation in this form, where I have a number to just the x power on one side, and then some number without any variables on the other. So here's what I mean by that. So on the left side you have 6 to the x plus 3. On the right side we have 8 to the x. 6 to the x plus 3, that's the same thing as 6 to the x times 6 to the 3. Right, that's when you add powers, is when you multiply things at the same base. And then on the right side I still have 8 to the x. And then I get all this stuff with just the x power to one side, so I can divide both sides by 6 to the x. Now 6 to the third power is 216. That's 6 to the third power. Equals, and then on the right side, 8 to the x divided by 6 to the x. But remember, when you divide things with the same exponent, you can combine the bases. This is the same thing as 8/6 to the x. And 8/6 is really 4/3. So I have 4/3 to the x power equals 216. And this is exactly what I was talking about here. I use properties of exponents to get some number to just the x power equals another number. And then we change to log form. Change to the equivalent log form, and then you have your solution. So x here, remember the exponent is the logarithm. X equals the logarithm base 4/3 of 216. Now if you don't like this, you can use the change of base rule. Change this to natural log of 216 divided by the natural log of 4/3 and punch that in. And you're going to see that this is exactly the same solution. It's going to round, it's 18.7. So over here, right, let me punch that in, right? Natural log of 216 divided by the natural log of 4/3. And you see it's the exact same number. 18.6847875569, blah, 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 blah. So yeah, just a couple ways of doing the same thing. You're finding a solution to some exponential equation, eventually using logarithms at some point. Now back on the assignment, like I said, they said enter an exact answer, so the answer the way it looks with all the logs, or round your answer to the nearest tenth, which I said rounded to 18.7. I'll put in the answer to the nearest tenth. That'll be a lot less typing. So you can enter the answer with all the logarithms, or round it to the nearest tenth. Again, I'm going to do the nearest tenth here because it takes less time to type. All right, and then after you submit an answer, you'll be told if you're right or wrong, and then given some sort of answer explanation. Please read through the answer explanations. See, they're doing the exact same thing I did the first time around. Oh, except they have, they took everything, they took the x's to the left and subtracted 3 times the natural log of 6 to the right, and still read through the answer explanations though, right, just to make sure you understand why something was right or wrong, and hopefully you can learn from your mistakes for the future. Okay. so now we're back to this, use like bases to solve exponential equations. And this also kind of ties into the use the they don't have a one-to-one property thing, but this is involved. Remember how there was a one-to-one property for logarithms? There is a similar property, one-to-one property for exponential functions. So I'll write that out. Alright, but this time I'm not going to draw the graphs like I did with the logarithms. You can look at those on your own. But the one-to-one property for exponential functions, right? If b to the mth power is equal to b to the nth power, then m must be equal to n. This is it. Because exponential functions are one-to-one. Alright, they pass the horizontal line test. Two different inputs give you two different outputs. Or in other words, if two outputs are the same, their inputs must be the same. That's exactly what this is saying. So if we end up with equations where both sides are a single base to a single power like this, and they have the same base, well then they must have the same powers. That's all this is saying. And that's what we're asked to use in this objective. So for example, they have a 3 to the 8x power equals 3 to the x minus 5 power. Notice that these have the same base, and it's a single base to a single power, right? There's not some sort of multiplication or addition or subtraction or division going on, but they have the same base, right? And you notice I didn't do this property in the last example, right? The last problem, because these had different bases. Base 6 on the left, base 8 on the right, so you can't use the one-to-one property there, right? You can only use the one-to-one property if it's basically if the equation's written like this: b to the m equals b to the n, same base to some power on both sides. So by that one-to-one property, then 3 to the 8x is only going to be equal to 3 to the x minus 5 if 8x is equal to x minus 5. And then we solve this. So just equate the powers when you have the same base on both sides, only when they're the same base, of course. And then subtracting x, we have 7x equals negative 5, dividing by 7, x equals negative 5/7. And then of course check your solution, but I'll tell you this right now. Remember the domain for exponential functions was all real numbers? So if you know you did everything right, these should be good. I mean, if you plug in negative 5/7, you'd have 3 to the negative 47ths on the left side, and then negative 5/7 minus 5 would be negative 47ths as well, 3 to the negative 47ths. You have the same number on both sides. But the domain of exponential functions is all real numbers, so no matter what you get, you should be able to plug them in back to the original equation and get the same result. It wasn't like logarithms, right? Logarithms, you can only have positive numbers inside logarithms, so you really had to check those. You should still check these solutions, but if you feel like you did everything correctly, you probably did. Right? Yeah, so the only solution to this equation here is negative 5/7. Great. Okay. Yeah, so this is solve an equation with a base e using natural logarithms. So I want to get the base and exponent alone, basically. If you see a base and exponent, and that's the only base and variable exponent, get that alone, and then you can change to the equivalent logarithmic form. I'll show you what I mean with this equation here. So I have 6 times e to the 4x power equals 14, whereas to solve for x, I'm only seeing one part of the expression on either side with a base that has a variable power, a power with a variable in it. So we're going to isolate this. Isolate base and variable exponent and variable power. Right. Now to do this, this e to the 4x, I want to get that alone. It's being multiplied by 6 right now, so I just divide by 6. We have e to the 4x. Now 14 divided by 6 is 7/3 when you reduce it. That's the same thing as 14/6. And now I have base to a power equals some number. This is an exponential form. If I want to solve for that variable and I want to get it out of the exponent, so you change to the equivalent log form. You change to logarithmic form. Remember, the exponent is the logarithm. 4x equals the log base e, which is natural log of 7/3. And then to get x alone, then you solve this equation. Then to get x alone, we divide by 4. X equals the natural log of 7/3, whatever that is, divided by 4. And we are asked to round to the nearest tenth. So I'm going to punch this expression into my calculator and round to the nearest tenth, right, 1 decimal place. So the natural log of 7/3, and then that expression divided by 4. And rounding to the nearest tenth would be 0.2. So the solution to this equation is approximately 0.2. Okay, submit. Great. All right. Next question. All right, so we're here on this objective. Rewrite equations so all powers have the same base and solve exponential equations. So this is going back to that, trying to be able to use that one-to-one property. I want to use this property here eventually for some of these equations, a lot of these equations. So trying to get both sides to be the same base to some power, and then, the only way that's going to happen is if the powers are equal, and then we set the powers equal to each other and solve and check. Right? So this equation, now this is going to involve use of some properties of exponents, which I'm assuming you know. Right? I'm not going to go over all the properties of exponents. So like here we have 64 to the x minus 1 power equals 16 to the 2x minus 2 power. Now you could do this the way I did the very first question in this video. Take the natural log of both sides, pull the powers out, solve for x, and whatever. But you notice how both sides have a base of, this has a base of 64, this has a base of 16. These are both powers of 2. They're also both powers of 4. Right? 64 and 16. These are both powers, nice whole number powers of 2 or 4 if you want to use 4. And I'll show you both. You end up with the same result both times. So if I want to use 2, so instead of 64, I'll make that 2 to the 6th. Alright, that's 64 as well, to the x minus 1, and then equals, and then instead of 16, I'll make that 2 to the 4th. That's also 16 to the 2x minus 2. And then we use some properties of exponents. Remember, when you raise a number to a power and then that to another power, you multiply the powers. So this would be 2 to the 6x minus 6 power. Right? You would distribute the 6. 6 times x minus 1 would be 6x minus 6. And then over here, same thing. This would be 2 And then 4 times 2x minus 2 would be 8x minus 8. All right. And now I can use that one-to-one property. Now I have it set up where both sides have the same base to some power. So by that one-to-one property, I'll just write 1 to 1 here. The powers must be the same. 6x minus 6 must be equal to 8x minus 8. And then if I subtract 6x, I'll have 2x on the right. If I add 8, I'll have 2 on the left. And then x must be equal to 1. All right, and then again, of course, check it back. You'd have 64 to the 0 equals 16 to the 0. That's 1 equals 1. That's all. That's true. You'd have 1 equals 1. This is a good solution. Now, again, that's not the only way you could have done it. Said, oh, these are both powers of 4. 64 is 4 cubed. So I write 4 cubed to the x minus 1. And 16 is 4 squared to the 2x minus 2. And then do that power to a power property. This will be 4 to the 3x minus 3 on the left. This will be 4 to the 4x minus 4 on the right. And then I can apply that one-to-one property and say 3x minus 3 must be equal to 4x minus 4, so x must be 1. I just add 3x, subtract 3x and add 4, and get the same solution. It really doesn't matter which way you do it. And like I said before, say you didn't see that, you could do this the way I did that the very first example in this video with the natural logarithms and stuff, and you'd end up with some expression that does simplify to 1, but that might be a little more involved. All right, so back in the assignment, x equals 1. Great. Okay. So back to using logarithms. So here again, we're given two sides with different bases. So this is like the very first example I went over. And now I prefer the second method I did, where I use properties to get everything with a power of just x, some number with a power of just x on one side and then some number on the other. Or you can do it the way they're showing you with the logs on both sides. That was the first method. All right, so once again, I'll write this out. So on the left side, we have 9 to the x plus 5 power. On the right side, we have 6 to the x. 6 to the x. And like I said, I like doing this property stuff. This is the same thing as 9 to the x times 9 to the 5 equals 6 to the x. Then I can divide both sides by 9 to the x. So 9 to the 5th equals 6/9 to the x, which is the same thing as 2/3 to the x. So I have 2/3 to the x equals 9 to the 5th. And then I can change this to log form if I want x alone. Change this to logarithmic form. And now we have x equals the log base 2/3 of 9 to the 5th. And I'm pretty sure that this will be acceptable. Now I'm going to use some properties here. Do some change of base. Change it to natural log. So this will be the natural log of 9/5 divided by the natural log of 2/3. And this is fine too. If you want to use some more properties, this numerator has a power. You can pull the power out. That's 5 times the natural log of 9 divided by, and this denominator log has a fraction in it, so I could use the quotient rule, natural log of 2 minus the natural log of 3 in the denominator. And I'll enter this. Now you could also, again, round to the nearest tenth. Round to the nearest tenth. I'll put any one of these in my calculator. So back up here. It was, what's the log, base. I can't put fraction bases in, that's not good. So I'll just do natural log or 5 times the natural log of 9 divided by the natural log of 2/3. And rounded to the nearest tenth would be negative 27.09, so negative 27.1. Rounds to negative 27.1. Great. And again, you can go through the whole natural log deal that they have here. Like, again, the very first example I had in this video did it this way. I did it this way as well. You choose, right? As I said, I personally prefer using properties of exponents to try to write a number to the x power on one side equals some number on the other side, and then changing to log form, and maybe using change of base rule after that. But yeah. All right. All right. So this one is, again, when you have a base with a variable power, and that's the only one, get that alone and then change to log form, right, and solve. All right. So here we're asked to solve 5 times e to the 3x power equals 22. Okay. So first I want to isolate this e to the 3x. So I'm going to divide by 5. So e to the 3x equals 22/5, right, or 4.4. And then change to logarithmic form. I'll just put log here, log form. So 3x would be equal to the log base e, or the natural log, of 22/5, or 4.4 if you want to write a decimal, and then divide that by 3. And we're asked to round this to the nearest tenth again. So my calculator, the natural log of 22/5, or 4.4, divided by 3. And rounding to the nearest tenth is 0.5. This would round to a half. I don't know why I went there. I want to go to the assignment. To the nearest tenth, 0.5. All right. Next. All right. So this is another one of this objective where both sides have a base that's different, but they're both powers of some whole number. So it should be easy to change to have both sides be in the same base. Right, so once again, I'll write this one. Alright, so I got a lot of room on this paper. I'll just go over here. So on the left side, we have 5 to the x plus 1 power. And on the right side, the base is 625, and the exponent is x plus 1. Now, these have different bases. So, I mean, you could solve this just like I was solving earlier problems where there was a different base on both sides. But one thing I noticed is that 625 is a power of 5. It's actually 5 to the 4th power. So on the left side I have 5 to the x plus 1 power. And on the right side I'm replacing 625 with 5 to the 4th, and then that's being raised again to the x plus 1 power. So we have 5 to the x plus 1 on the left, and then power to a power, you multiply those powers. This will be 5 to the 4x plus 4. Right, 4 times the quantity x plus 1 would be 4x plus 4. That's on the right side. And then I can apply the one-to-one property. Right? These have the same base. Single base to a power equals single base to a power, same base. So the powers must be the same. X plus 1 must be equal to 4x plus 4. So that means 3x must be equal to negative 3, right? I'm subtracting x, subtracting 4, so x must be equal to negative 1. And then if you check that, you'd get 1 equals 1. 5 to the 0 equals 625 to the 0. And that works. So -1 is our only solution here. All right. Okay, next. So use like bases. Now this is one where they're already set up to where you can use the one-to-one property immediately. So once again, I'll just quickly write this one out. This should be a fast one. Because the left side is 4 to the 4x power equals, the right side is 4 to the x plus 10 power. You know, and these are already set up the way that I want. You know, both sides already have the same base. So I can apply that one-to-one property and say, hey, you know, the powers must be the same then. 4x must be equal to x plus 10. So then subtracting x, you got 3x equals 10. Dividing by 3, x must be 10/3. And there's your solution. Right? The value of x must be 10/3. And of course you can check that by plugging that back in for x in the original equation. See that you get the same number on both sides, but you know, you should. Okay. So same objective. Alright, so this one I'm just going to kind of speak out loud. I'm not going to write this. These are the easy ones where, you know, they both have a base of 7. Both these sides, both of them are 7 to some power. So the powers must be the same. 12x must be equal to 2x minus 2. I'd subtract 2x to have 10x equals -2, and then divide by 10. X equals -2/10 or -1/5, right? When you reduce it, -1/5 or -0.2 if you want to write a decimal. Wonderful. All right, then looks like one more of these. Again, both sides have base 7, so the powers must be the same. 2x must be equal to x minus 3. Just subtract x from both sides. X must be equal to -3. That's it. -3. Wonderful. Yeah, so that's probably the easiest of the objectives, right, where both sides are already written in the same base. You just have to equate the exponents, solve, and check. Alright, so back to a problem where both sides have different bases. Now again, you can do it the way they're showing you in the answer explanations, or that very first example I did in this video, the first method. But like I said, I honestly prefer using properties of exponents so that I get, you know, just a number to the x power equals a number. That's what I want. All right. So we have 6 to the x plus 3 equals 3 to the x. You know, this is 6 to the x times 6 to the 3 equals, you know, just 3 to the x. Divide by 6 to the x, and then I'd have 6 to the third power on the left equals 1/2 to the x on the right, right? Because it'd be 3 to the x divided by 6 to the x. 3/6 to the x, or 1/2 to the x. So then changing this to log form, I'd have x equals the log with a base of 1/2 of 6 to the third power, or 2/16, right? 6 to the third power, we saw that earlier. And if you want, you can do change of base rule. Say I do natural log instead. Natural log of 6 to the third divided by the natural log of 1/2. And we could use properties here if we want. Pull the 3 out with the power rule. That'd be 3 times the natural log of 6 in the numerator. And then the natural log of 1/2 would just be negative natural log of 2. Because that's 2 to the -1, pull the -1 out, or the natural log of 1 minus the natural log of 2, 0 minus natural log of 2, same thing. So there's an exact answer. And they said you can enter this, or enter your result rounded to the nearest tenth, which I will do. All right. So back here, I can actually enter this log, originally I had log base 1/2, I'll put 0.5 for the half of 6 to the third, 216. That's our solution. And you can put in the other ones I had too, with the natural logs, and it's the same number, negative 7.75, so negative 7.8 if I'm rounding to the nearest tenth, negative 7.8. Great. And again, they do the thing where they take the natural log of both sides, pull the powers out, then solve for x like a linear equation. Same stuff. Okay. Alright, so one more like this, where both sides have a different base. I'm going to solve it the way I've been solving them, the way I like, with the properties of exponents to get a number to the x on one side and then just some number on the other side. Then I change the log form and use the change of base rule after if I need to. So 8 to the x plus 6 power equals then 5 to the x. Again, power is being added here, so this is 8. This is equivalent to 8 to the x times 8 to the 6th equals 5 to the x, and then dividing by 8 to the x, I'd have 8 to the 6th equals 5/8 to the x power. And then I can change to log form. The exponent here, x, would be equal to the log base 5/8 of 8 to the 6th power. And I'll use some change of base rule. I'll change this to natural log stuff. So this is the natural log of 8 to the 6th divided by the natural log of the original base, 5/8. And if we want to use some properties, I can pull the 6 out here. This would be 6 times the natural log of 8, power rule. And then the log of a fraction is the difference of logs. I can write the denominator as the natural log of 5 minus the natural log of 8. Okay, and there you go. I can type this in or round it to the nearest tenth. I'll punch this in my calculator, this last expression, and see what we get. So numerator was 6 times the natural log of 8 divided by the denominator was natural log of 5 minus the natural log of 8. So our solution, rounded to the nearest tenth, be negative 26.5. Negative 26.5 to the nearest tenth. Great. And again, please read through the answer explanations. They may do it in a different way, and if you like that way better, keep doing it that way. All right, next. So this is one again where both sides are a different base. So I could solve this the way I've been solving these other equations where the sides have a different base. But the nice thing about these bases is that they're both powers of the same number, the same whole number, right? Like 8 and 4, they're both powers of 2. So I could easily write both sides with base 2 and then use the 1-to-1 property. So I'll do that here. So left side we have 8 to the negative 4 power. The right side we have 4 to the negative 2x minus 4 power. Like I said, both of these bases are powers of 2. 8 I'm going to replace with 2 to the third, and then that's being raised to the negative 4. And then 4 I'm going to replace with 2 squared, and that's being raised to the negative 2x minus 4 power. And then power to a power, you multiply those. So on the left side I have 2 to the negative 12th power, right, 3 times negative 4. On the right side I have 2 to the negative 4x minus 8 power. Right, that's 2 times the quantity, negative 2x minus 4. And now I have it the way I want it if I want to use that 1-to-1 property. Right, both sides are an expression with the same base, so their powers must be equal. So negative 12 must be equal to negative 4x minus 8. Then I add 8. We have negative 4 equals negative 4x. Divide by negative 4. X must be positive 1. And you can check that out. It should work. The number on the 8 to the negative 4 on the left, 4 to the negative 6th on the right. Those do have the same value, especially if you change both to base 2. you'll see that they're the same. Alright, so solutions 1 here. Great. Alright, and one more of these. So once again, the sides have different bases, but the bases are both powers of 2 or powers of 4, as we've seen before. And again, you can change them to base 2, base 4, as long as they're the same base. You should be able to use that one-to-one property eventually. Alright, so here, the left side we have 16 to the negative x minus 4 power. On the right side we have 64 to the 2x power. And I'm going to use base 4. 16 is 4 squared, so I'm replacing that with 4 squared, and then that's raised to the negative x minus 4 power. And 64 is 4 cubed, so I'm replacing that with 4 to the third, and then that's being raised to the 2x. Then I'm using that power to a power rule, so the 4 to the negative 2x minus 8 power on the left side, and then 4 to the 6x on the right side. And now I can apply that one-to-one property. They both have the same base now, so their powers must be the same. Negative 2x minus 8 must be equal to 6x. And then, adding 2x gives me negative 8 must be 8x, so x must be negative 1. And again, you can check that. Should work. Alright, great. Alright. Now, one more objective to complete. So this is that one where you get, if you have that base and variable exponent in the equation, you want to get that expression alone first, and then change forms, change from exponential form to logarithmic form, and solve and check. All right. So the equation we're given here: 11 times e to the negative 4x power equals 21. So to isolate this base in power, I would have to divide by 11. So we have e to the negative 4x equals 21 elevenths. And then I would change to logarithmic form, giving me negative 4x equals the natural log of 21 elevenths. And then divide by negative 4. So the natural log 21 elevenths divided by negative 4. And I'll punch this in, and again, this is one of those where we're asked to round the solution to the nearest tenth again. So back to the calculator. So numerator, natural log of 21 elevenths, denominator, negative 4. And to the nearest tenth, that would be negative 0.2. It's 1/6, so I'd round to 0.2. So negative, don't forget the negative signs, right, when you need them, negative 0.2. Great. Alright, and there should be one more of these. I'll probably just talk this one out and punch in the calculator. Here, 5 times e to the 6x equals 31. First, you would divide by 5, then write the natural logs, log form. 6x equals the natural log of 31 fifths, and then divide by 6. So it'd be the natural log of 31 fifths, and then divided by 6 when you finally get x alone. And rounding this to the nearest tenth is clearly 0.3. So the solution rounded to the nearest tenth, 0.3. Wonderful. And that should be it for this preview version of this assignment. And like I said at the top of the video, the questions I saw here may not be the same questions that you see when you work on the assignment yourself, but the objectives are the same. The structure should be similar. So I'm hoping that watching me do these here helps you in some way when you're working on the assignment on your own. And thank you very much for watching.